about to. I
Yes,
think
yes, now it's coming. Yeah. Can you just move slides? So that,
yeah.
move the slides.
This is fine.
Yeah, it's coming. Okay, okay, fine, fine.
Video
Okay,
also.
good. Yeah. And switch on video also once so that
Yes, yes.
everything we can make it clear.
You see the
Yeah,
video?
yeah, yeah, yeah. Yes.
Great.
Also switch on. Yeah, fine. So there is no problem because sometimes we get some problems.
Right.
Right. Okay, fine. So everything is set. We are waiting for the participants. Let's wait.
Okay. Then,
Okay. Yeah, I posted the link in various groups actually just now. So hopefully the students will join.
Yeah. ఏంటి సార్ నా
Actually,
ప్రాబ్లం వచ్చిందా?
లేదు సార్. లింక్ ఇందాక యాక్టివేట్ కాలేదు.
అవును.
అది యాక్చువల్గా 7 to 8 ఉంది లింక్.
అవునవును.
యాక్చువల్గా అది మన ప్రోగ్రామ్ 6 to 7 అది సార్ హోస్ట్ కానీ ముందు లాగిన్ అయితే సరిపోతుంది. యాక్చువల్గా దానికి కూడా ప్రాబ్లం లేదు.
నేను యాక్చువల్లీ 5:45 నుంచి ట్రై చేస్తున్నాను సార్. మీటింగ్ హాస్ నాట్ స్టార్టెడ్ అని వచ్చింది. సో
అదే ఎస్ యాక్చువల్ దివాళీ ఎఫెక్ట్ కదా, స్లోగా జాయిన్ అవుతున్నారు.
అవునవును. అందరూ ఎవ్రీబడి ఈస్ ఇన్ ఫెస్టివల్ మూడ్.
ఎస్ ఎస్
I can also say.
Mr. Praveen, you are from now. You are in which place actually? Delhi, Gurgaon,
no sir, right now I'm in Trivandrum.
Trivandrum. Okay. Yeah.
Yeah, I was in Noida before this place. That was about 3 years back.
Okay.
Yeah.
And then Mr. Praveen, actually I request you maybe at the end of the session, maybe a few minutes you can spend. How the opportunity core opportunities will be there for students, like particularly in Schneider Electric kind of companies. You can give some kind of idea to them. Okay, and you can encourage them towards to settle in the core companies, like.
Yeah, sure sir.
Yeah, thanks. And one more thing, Mr. Praveen, actually, let me know. Actually, some of the sessions actually we are uploading in our IEEE website. Actually, we have the YouTube channel for our IEEE section. Okay, and whoever the speakers agree for that, and we are now uploading videos there. And if at all, if you have I mean restrictions for your lecture, we can upload there, and it's not mandatory, it's up to the speaker permission. You just think and then let me know after the session if it is can be open source, and we can make open source through YouTube, or if not, okay.
Yeah, sure, sir.
Yeah.
No problem.
Okay, yeah, I think slowly members are joining. I think we can start now. Sir Banu sir, Professor Banu sir, we can start
Yes,
now.
sir. Yes. Yes, sir. We'll start. Yes.
Okay, fine. Okay. Yeah, good evening to all of you, and I welcome all the participants of this program, and special welcome to our speaker, Mr. Praneeth from Schneider Electric. And we are now this event is organizing by IEEE Power Electronics Industry Application and Power and Energy Joint Chapter under Vizag IEEE Vizag Bay section. And we are conducting a series of lectures by eminent scholars and industry experts to reach out the student and faculty community to enhance their knowledge in technical domain and technical community particularly. So in this way, actually, we have organized this is a lecture by industry resource person by Dr. Praneeth, and I hope this topic also it's very important, and advanced SCADA, and it's very important role it has in smart grid application particularly. And the students particularly they can see this topic like some kind of what will be happen like the future of electrical engineering. So what are the advanced things they can get into of the different aspects of these advancements in future of electrical engineering. And any clarifications are there, and I will welcome the participant to interact with the speaker, so at the end of the session to clarify any doubts, and also they can explore the I requested already the speaker to spell out some of the important opportunities for students also, so they can also discuss in this regard. So now I welcome Dr. Praneeth and other participants to this event. Yeah. And now I request Dr. Ashwini to give a brief introduction about today's our speaker.
Good evening, sir. I, Ashwini RT from the Vankaila party for today's session on behalf of IEEE ES PLS IAS Joint Chapter. He is currently working as a technical lead for Schneider Electric. Was previously associated with GE Power, Tata Consultancy Services, and Cient Limited. He served for distribution utilities across the globe, including Australia, Europe, and the US, and for Indian state distribution utilities, including Kerala, Chhattisgarh, and Maharashtra. He worked on various platforms and systems across the smart grid infrastructure like SCADA, DMS, OMS, and GIS, and integrations between various distribution utility systems. So with this, so I warmly welcome Praneeth sir for today's session, and I also thank our Vizag section chair and members, and IEEE PES PLS IAS Joint Chapter Chair Dr. Sandeep sir, and Vice Chair Dr. CVK Banu sir, and Secretary Dr. Shankar sir, and Dr. Vakula madam for giving this opportunity. So over to Sandeep sir.
Yes. Thank you, Dr. Ashwin. Now I requested Mr. Praneeth to take over the session. You can present your screen, sir.
Sure, sir. Ashwani sir, thank you so much for the introduction, and thank you Sandeep sir and Banu sir for this opportunity and the warm welcome. I'll just share my screen. Let me know once you see it. I hope you are able to see my screen.
Yes, 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 yes. Yeah, your voice also clear and the screen is visible.
Great.
You can,
I just turned on my video as well, just in case.
yeah, sure, sure. You can.
Yeah. So we'll just get started. So this session is about an overview on SCADA and ADMS applications. Okay, so we'll see first at a high level, and then we'll try to get into some more details of it. Yeah, already the introduction has been given. So thank you so much for the introduction. And this is how I used to look 2 years ago when I last took my passport photo. And thank you for the introduction already. Well, let's get into the technical side of things. So we'll start with answering the basic questions of what, the why, the how of this SCADA IDMS. The other more trivial questions of where, when, who, and all, I leave it to you for Googling. They may not be that important. So we'll start with what is it. So as the abbreviation says, and probably you might already be knowing, SCADA is a supervisory control and data acquisition. DMS is distribution management systems. ADMS is advanced version of this DMS. So to see it in a very simple picture, you can imagine the field equipment like this on the left. So by that I mean your transformers, substations, conductors, etc. To the right, you have the control centers, centralized distribution control centers, where the distribution operators or load dispatchers sit and manage the distribution networks. So the communication that is happening between the field and the control centers, two-way communication. All the technology involved in this communication, you can say it is SCADA. Okay. ADMS is nothing but, okay, so I have made it a little bit more clear as well. So I have denoted SCADA with this envelope, that means for the communication part, and the DMS with his brain. So much of data SCADA is pulling in from field into the control center. How best to utilize the data? So add some intelligence to the data. That is done by the DMS application. So this DMS indirectly it acts as a support system to the distribution operators. Okay. So we saw what is it at a very high level. Now we are seeing why is it needed. First of all, we need to reduce outage time. So the lesser the power cuts we have today, the better, because electricity has become a basic necessity of life. So that is at our level, energy consumer level. Also for the utilities themselves, generation, transmission, and distribution people, they have to reduce the aggregate technical and commercial losses. So that, of course, it is a service, but something is being gained out of it as well. Okay, and also to improve the operational efficiency of our existing distribution networks. I think somebody has to mute.
Madam Sujata, I think you have to please.
Thank you. Next one is to reduce drive times. So previously, you may know that if there is some fault in the network or for some maintenance situations, the field crew had to travel a lot, travel through trucks or jeeps and all. So by using this system, a little bit of contribution is done to the environment as well, because the driving of those trucks is reduced. So that way pollution is also reduced. Also to reduce manual errors or misoperations, manually operating something else when meant to operate something else, those kind of situations can also be reduced. These days there's so much of data, so the need of having past, present, future data right on your fingertips, that is a need of the hour. So that is also possible with this SCADA IDMS applications. And finally, to increase the customer satisfaction, so directly or indirectly by reducing the outage times, plus increasing their engagement in all this infrastructure, indirectly the customer satisfaction is also increased. So these are some of the reasons why SCADA and ADMS are needed. how does this thing work? So I will answer it in two parts. So first of all, how does SCADA work? So to simplify things, I have shown your substation equipment here onto the left. So in general, you have the distribution substations where you have power transformers stepping down from 66 kV, 33 kV, etc. to 11 kV. And then from the 11 kV bus, you have individual 11 kV feeders emanating outside. So from there, there is some hardwiring done to these devices called remote terminal units. Okay, so these are the intelligent devices which facilitate for remote control and monitoring. Similarly, you have another device called multifunction meter. So that is connected through the CTs and PTs onto the 11 kV bay. So that is used for measuring the analog data like voltage, current, power factor, etc. flowing through that particular bus. So that way data is first read the remote terminal unit from the actual bay. From there, through some communication equipment, it flows out from the substation first to local area network. Then you have some communication paraphernalia. So through WAN, that is wide area network, for long distance communication, they are used. They are communicating to the centralized communication center, wherein there is one more router for receiving the data. Okay, and then you have some server computers, high-end server computers for processing so much of data that is coming from field. And then finally, you have the human machine interface where you have all these displays updating what is happening in the field. That is where the operators are interacting through the system to the field. So this is how at a high level SCADA works. How does DMS work? So we have already seen how SCADA works. So SCADA is pumping in data from field and it goes into this particular server called front-end processor server. Okay, so why this is called front-end processor is because it is acting like a front end of the whole field equipment in the control center. So through this front-end processor only, all your field data is coming. So that is why it is called front-end processor. So up to this part, you can consider it as SCADA. Apart from this, you have some additional computers that are doing some additional processing. So like I told you, DMS is the brains. All those processing activities done, additional processing is done in these additional servers. I have shown some important servers here. DMS server is where all your DMS applications will be installed. We'll see some important DMS applications in the future. Apart from this, we have one historian server. So this is for storing all the historical information. So why is it needed? One simple example I'll give. Suppose there is a circuit breaker connected to a particular feeder in a particular substation and it got tripped at a particular moment in time. And then immediately the fault has been found and it has been rectified, and then later on the breaker was closed at some other point in time. So what this historian server will do, initially when it was opened, it will store that along with the timestamp in a database. When it is closed, that information is also stored along with its timestamp. So with this, what happens tomorrow when you want to know on this particular breaker, on this particular day, what was the outage duration or how many times outages occurred. All those things you can identify from the help of this historian server. I just told you one example. Like this, there are multiple other scenarios. So this is about the past scenarios. So what if, so there is another requirement of doing some what if studies. So what if some 10 more transformers get, or distribution transformers need to get added to some existing 11 kV feeder? How does the loading pattern change on that feeder or transformer or substation? So those kind of future or what if studies can be done using this simulation server, where you can simulate the future conditions and see what are the outcomes that are going to be. So all those kinds of processing are done here, and then finally the output is seen in the HMIs where the operators will sit in front of. Okay, so that is how DMS works. Individually, we have seen how SCADA works, how DMS works. So overall, as a distribution control center, which includes both, this is how it looks at like a high level. So you have the communication happening from outside through the communication equipment called routers. Then you have firewalls in between. These are actually cyber security equipments. So they monitor all the network traffic that is flowing from outside into the control center and vice versa. So why this is needed is to avoid any cyber attacks. So generally in these firewalls, we pre-configure from what locations data has to come. So suddenly if from some new location somebody is trying to access, it will detect it and stop that access. So it is like it is detecting and preventing intrusions and some other malicious attacks that these days people try to do. It tries to prevent those kind of things. And then you have the different servers. So generally you have server racks like this. Servers are nothing but high-end computers. Okay, so multiple servers you have placed into racks like this. Okay, and you have separate storage devices for storing all your historical information. This is there because you can just use them like your old day cassettes or CDs. Once it is filled, you can remove that, store it somewhere else, put one new disk, and keep storing more data. Okay. And then through networking switches, they are all this process data and all the communicated data is shown to the operators in front of their screens. Okay, so what all you see here is the brain where all the processing is happening. So this is in the server room or networking room, which is separately placed. And what is happening here is the eye. So this is where your operators, distribution and transmission operators will sit, and they will monitor and control the distribution or transmission network. So this is your control room, this part. Okay. So like I told you, ADMS is an advanced version of DMS. So it is nothing but an amalgamation of different technologies and software. So ADMS includes SCADA, it includes DMS, and optionally it includes OMS and EMS also. So at a high level, again, we'll see what are all these four things. SCADA, like we already told, it is a technology that is used for monitoring, collecting, and processing data from field devices and controlling them remotely. Okay. What is DMS? DMS is a brain behind which processes all this data. So it is used for analyzing, controlling, optimizing, planning, organizing your distribution network, and it shows you intelligently the whole distribution network in its current scenario in front of your screens, operator screens. Okay. What is OMS? OMS is outage management system. It is used for predicting and locating outages, effectively managing the field crews, and improving the customer engagement. So the overall aim of OMS is to reduce the outage times. Okay. What is EMS? EMS is energy management system. So that is also similar to DMS. Main difference is this is used for managing transmission and sub-transmission networks, and DMS is used for managing distribution networks. Okay. So this is also used for visualizing, operating, optimizing, and maintaining transmission and sub-transmission network. So yeah, so those are ADMS is made up of all those things. So how did we end up into all this SCADA, ADMS, and also if you see at a very high level, what is the story behind all this? Initially, electricity was invented, and it was starting at the starting stages used only for heating and lighting purposes, and then its importance grew, and now it has become a basic necessity of life, like your food, water, etc. Because whatever you do, almost everything of it involves electricity in some way. So it has become a necessity. So you can see this graph, the per capita consumption of electricity has drastically increased in the past 16 years itself. So you can imagine about how much it would have increased from the previous times. So it has become a necessity. Then slowly electrical grids came into picture to cater for so much of a necessity to make it a service. Then these grids started becoming larger and longer. They have grown enough in size so that they had to get interconnected. Then again, the distribution networks internally, previously they used to be radial. Then they had to get converted into rings. So we'll see at a very high level what those are. And then like everything else today, even the grids are getting smarter. So that is how your transformation has occurred from when electricity was initially invented to how it is there right now. So when you talk about the evolution of SCADA, initially probably around 1950s or 60s with the birth of computing, SCADA was also introduced into the power utility industries. Initial days, it was called monolithic SCADA. Everything was centralized. All processing was being done in the control center itself. And there was only the feasibility of single RTU per substation. So you remember RTU is remote terminal unit. So that is the intelligent device that facilitates all these things, control and monitoring. So this drawback was there initially, only one RTU per substation. And then when you talk about the control center side, there were very bulky mainframe machines which were huge in size. So managing them was not very easy. And the protocols of communication between the RTU and the control center was proprietary in nature. So it was all vendor specific. So we had to run around different vendors for different issues. Then it got evolved a bit, and the second stage was called distributed SCADA. So here it started to become decentralized. So some part of the computing was done in the substation itself. Some part of it was being done in the control center. So that is decentralized computing. And then with the birth of local area networks, so this is part of communication. So with the improvement in communication, there was this advancement so that you could connect multiple RTUs per substation, so that you could have more number of controlling and monitoring equipment per substation. Also in the control center, the machines became smaller, so managing those things would have become easier. Okay, and birth of LAN also gave rise to human machine interfaces, so that operators could easily visualize things that are happening in field, and more functionalities arose out of it. Okay, and what you see next, that is network SCADA, is what we see currently. So we have very advanced communication technologies right now. So that has helped a lot in this evolution, and everything has become open and standardized. So right now you can buy an RTU of any vendor, you can buy a SCADA of any vendor, everything can communicate with everything because nothing is proprietary. Everything has to follow a standard. So there are some standard protocols devised by IEC. So all the vendors have to follow those protocols. So because of this standardization, integrations also became easy. So now you can integrate so many applications, so you can make use of the data, so much of data coming in from field in different ways, in different systems. That is how SCADA had evolved. So we were talking about the radial and ring distribution network. So I'm sure you already know what this means. But again, at a high level to discuss, so you have your distribution substations where the voltage is stepped down to 11 kV, and you have the 11 kV feeders emanating. So initially, you had these feeders going in radial way, so they'll go up to so many kilometers and stop. So with this, initially SCADA was enabled only for substation. So the controlling equipment was there only in the substation, and SCADA was used only for monitoring and controlling this equipment. Okay. One big drawback here was that fault in any one section of the feeder will give rise to an outage that has to be borne by everyone in the feeder. So for example, there is an outage in this section. So obviously our feeder breaker will trip. Okay, and until and unless this fault is cleared, everyone connected to this particular feeder, they will be under an outage. So that is not a good thing. Then came the ring networks. Okay, so in the ring networks, you could merge two radial networks to form a ring or necklace or whatever notation you take. So with that could be done with the help of a particular equipment that people could install in the field, in the distribution network outside the substation. So with that, SCADA was enabled not only for the substation equipment, but also for some of the equipment in this new device, in this new equipment. Okay. So one big advantage with this is that fault in any one section of a feeder can be isolated, and customers connected in other sections could be re-energized immediately. So if there is a fault in this section, with the help of this new equipment, you could just isolate this particular section and immediately restore supply to the other customers, so that they are not under any outage. So that is a big plus. Okay. So what is that equipment? That is nothing but a ring main unit or RMU. So RMU is also a type of switchgear which is compact, sealed and enclosed in nature. So it is not very bulky in size. So generally it is used in medium voltage networks, that is 11 kV, 6.6 kV, etc. based on the country. Another big advantage is that it has all this protection equipment. It has the air or oil or gas insulation chambers. And the main advantage of this is it is modular and extendable in design. So initially, if you purchase an RMU, which is a 3-way RMU, one incoming and two outgoing. So tomorrow there is a change in the configuration and you may have to add one more outgoing limb. So that could easily be done in case of these RMUs. You don't have to throw it away and buy a new 4-way RMU. You can just add one more limb to the existing 3-way RMU. So that is a very big advantage. Okay, and installation is easy and the maintenance is low. Okay, so this is how your typical RMU looks like. Okay, so day by day the size of the RMUs are also getting reduced with the advancement in technology. And this is how the single line representation of an RMU is generally done. Okay. So this is this example I have shown for a 3-way RMU. So one incoming, the other outgoing, and the third one going to your distribution transformer. So this is denoted by a load break switch where your main feeder line is connected, another load break switch where the outgoing feeder line is connected. This is a circuit breaker where your distribution transformer is connected. Earthing facility is also provided to the load break switch limbs. Plus, one more device called fault passage indicator is also attached to these limbs. So what this fault passage indicator will do is it will help in fault detection. So whenever fault current is passing through this fault passage indicator, so it will immediately blink or it will give some indication to the control center saying that fault has been passing through that particular location. So for locating a fault becomes very easy with this particular device. We'll see in more detail how that is done. Okay. Initially, when we started talking about SCADA, we saw that SCADA was there only for in substation, and then these RMUs got added. So because of that, more data is coming in from field. More data is coming in means more computing has to be done, and since more data is available, there are more possibilities for how best you can make use of the data. Okay, so typically SCADA systems initially were pumping data only from substations, and they were only used for remote monitoring and controlling. But with the addition of RMUs into the network, a whole new avenue of applications and use cases popped up. Apart from the increase in so much of data also is getting added in. Okay, and because of these RMUs, we are meshing the distribution networks more. So complex load flow equations were created because of this large mesh network. Okay, and also because so much of data is coming in, and because of these new possibilities, the need for past, present, and future data scenarios also increased. So these are all some new requirements that have recently popped up. Then entered your distribution management systems. So how this is solving all those previous requirements was sophisticated control center architecture with many high-end servers and large storage devices for sharing the computing and storage capabilities. So much of data is coming in. So to store so much of data and to compute on so much of data, you need to have high-end servers and more number of servers. So the new control center architecture is taking care of those requirements. Integration with the geographical information systems helped in easy visualization of RMUs and your distribution network. So now your distribution network has become very meshed and messy. It has gone into various directions, but with the help of GIS integration, now in DMS itself, you are easily able to visualize which RMU is where, which transformer is where according to its geographical location. You can easily map it onto your screen so that you won't get confused. Okay, and then powerful load flow algorithms were developed specific to distribution networks. So initially, all the load flow algorithms were developed for energy management systems, which are not so complex in nature, the networks. Okay, but because of these RMUs, the complexity has increased, and new powerful algorithms were developed specific to distribution networks also to solve the complex load flow equations. And historian and simulation capabilities were developed to cater for the past and future scenarios, like we saw in the first slide. Okay, so that is how distribution management system had cropped up and solved some of the problems posed initially. So again, if you zoom out and see at a very high level the transmission and distribution grids. So you have your generation happening somewhere in the generation plants, far away from urban areas. Then it is stepped up to some very high voltages for long distance transmission. Then once it is reached near the urban areas, it is stepped down in the distribution substations to 33 or 11 kV based on requirement. And then before it reaches our homes, it is further stepped down in the distribution transformers to 400 or 240 volts into the LT level. Okay. So you can see the coloring. So this part of the network is managed by transmission SCADA and energy management systems. This part of the network is managed by distribution SCADA and distribution management systems. And this part of the network with some additional inputs from the distribution networks is managed by the outage management system. Okay, so this is how your overall ADMS is taking care of different networks. So how and why did ADMS come from DMS? So initially you had so many field devices. Through transmission SCADA, field devices were communicating to a separate energy management system. Through distribution SCADA, your distribution substations and RMUs were communicating to a separate DMS application. And not through field devices, but some other integrations like advanced metering infrastructure, etc., or energy consumers like us calling in on the phone and telling that there is an outage at their end. Some data going into the outage management system. Okay, so everything was from a different vendor. Everything was a different application. Everything was vendor specific. Each system had its own database type. Everything had its own structure. And because of that integration, if there is a need for integration between any of these systems, specific expertise was needed. Okay, so that was a disadvantage. Then the concept of ADMS had come in. So big companies like GE, Schneider, etc., they came up with a one-stop shop solution which took care of all these needs. Okay, so this ADMS is a single application which encompasses different modules like SCADA, EMS, DMS, OMS, etc., into one single application suite. And since it is modularized, you can only buy which module you want. So, for example, your distribution utility is separate, they can only buy SCADA and DMS. But tomorrow, if they want to increase their portfolio, they can also go for OMS modules. Everything becomes very cost effective and also easy to scale up in future. So that is how your ADMS came up from DMS. So today what you are talking about is more of ADMS than DMS. So everything is under one single suite, product suite. So now we have started with the basic questions of what, how, and why it is needed. So then we talked about the evolution of SCADA, evolution of DMS, how they came into picture, what all problems they have been solving, etc. So now let us talk about some of the basic or advanced features. So while we talk about these things, you will get some more answers to those three questions of what, why, and how. Okay. So we'll start with features of SCADA. So we'll talk about the obvious ones first. So obviously it is used for remote communication. So this remote communication can be done in different ways. So one of them is host poll. Generally, this is used where your control center is polling the data. So control center is requesting for data from all substations and RMUs, and they are obliging. So that is the first type. Remote poll is reverse. Substations, RMUs, they are pushing data on their own and control center is receiving it. Third one is listen only mode. So this is generally used when you are upgrading your existing SCADA. So you have an existing SCADA application which is running since the past X years. So you want to replace it with a better version. So rather than doing it on one fine day, you'll make both the systems running parallelly so that you gain confidence on the new system. So that time the new system will be running on listen only mode. It's like read only mode. So it is getting data from field, but it is not doing anything. So you can compare both the old and new systems to see if there is any difference. Cry out mode is a very specific case wherein you want your substations or RMUs to report data only on particular alarming or difficult situation. So they are crying out, kind of. So only in that situation they communicate on their own. So that ways you can configure your remote communication. Then when you talk about data acquisition, status information can be acquired from field. Status information of a breaker or isolator or fault passage indicator, like whether it is open or closed, or is it in a set condition or reset condition, whether it is grounded or not grounded, those kind of data you can acquire from field. Analog data can be acquired, like what is the voltage value, what is the current value, what is the real power, power factor, reactive power, etc. Those kind of things you can also read from field. Analog data means you are reading the current value. What is accumulator data is? Accumulator is the data that is cumulative. Like for example, the total energy imported or total reactive energy imported, reactive energy exported through a particular period. Those kind of things which are cumulative, you can also measure them with the help of this data. Calculated points, we'll see in detail in the coming slides. Then manual points, so you don't have to have this communicating equipment everywhere in the field. So for example, there can be some substations or some RMUs where there is no remote communication enabled, but still you can manage them in the control center. Only thing is you cannot do any remote operations. You have to send someone to their field crew there and they have to manually operate. So once they operate it, that change will be manually reflected by you in the control center. So that is manual. With respect to status and analog points, whatever is happening in field is automatically reflected. Manual points, there is no communication, so you have to do it manually. But still you can manage them in the control center. And you have this manual override feature also. So for example, because of some communication issue, your substation or RMU stops communicating, and during that time, something got tripped. Okay. So to mimic that exact field condition in the control center, you can manually change the status of that particular breaker in the control center. So you are manually overriding what is coming from field. Similarly, if there is something wrong with the equipment and is giving you the reverse data by mistake, so you can still manually override it when you know what is the right thing. So that is this feature. That is about data acquisition. Next is about supervisory control. So you can control single state devices like your fault passage indicators. So generally fault passage indicators will be in either set state or reset state. Set will be automatically done when fault current passes through. You cannot set an FPI. So you can only reset an FPI. So that is single state points you can control. You can control two state points like opening or closing an isolator, etc. You can control set points like transformer tabs. Current position is tab position 2. You can change it to either 5 or -2 or whatever. Then you have the select before operate option. So that is for additional security. So like I told you, to prevent misoperations, the operator will select a particular device before operating it. So it happens in 2 steps. So in the first step, after he selects, he can confirm whether he is selecting the right device in the control center. Similarly, when he selects, the control to that particular device in field is locked to that particular operator, so that another operator cannot operate in the same time. So that way it is securing the operation. Okay. Then your typical displays look like this in SCADA. So this is a substation internal display, one example. So here you see the status information is represented like this in different symbols. Okay, so these are breakers actually, circuit breakers. So whether they are closed or open will be shown by different colors and different symbols here. Okay, and you can also see some numbers here. These are the analog data like current, voltage, real power, reactive power, etc. They are also changing real time based on the changes that are happening in field. So that is how you can easily monitor everything that is happening in substation remotely. Similarly, you will have different displays for different substations. So centrally you are managing a number of substations and RMUs. Okay. And in this displays itself, you will have some shortcuts for easily giving commands and doing various other functionalities. That is something advanced. So what you have seen here is the information that is coming in from field in a graphical view. In the same way, you can see all that information in a tabular view also. You will have one table containing all the statuses. Circuit breaker 1 in substation 1 closed. Circuit breaker 2 in substation 2 open. So like that in a table, currently what are their values? You can see everywhere, every breaker status, every other device status in one single table. Similarly, analog data, voltage, current, etc. at different points in one single table, etc. Okay, so all the data that you see here graphically, you can see in tabular format also in summaries and reports. So another advantage here is that you can take can export of these tables and use it for various purposes. You can print it for further deliberation with other operators, etc. All those things you can make use of. Then another important feature with SCADA is the alarms. What are alarms are actually any changes in the network that need special attention of the operator. Okay, so a particular breaker getting tripped because of a fault. Okay, so that really needs attention of the operator because he needs to attend to that fault immediately. So with the help of this alarm, he will immediately be notified that something wrong has happened in the network. So many other scenarios like that. A transformer getting overloaded or a feeder conductor running at maybe say 80% or 90% of its loading capacity, those kind of things. Okay? All those things will generate alarms and the operator can take measures accordingly immediately before the actual mishap happens. Okay. So the alarms are something that happens in the display along with the sound also. So you can see on the display some blinking or something plus sound also coming up to denote that something is wrong with this particular device or this particular substation or this particular location, and with the sound also. Okay. And again, these displays and sound options are configurable. So for example, your substation breaker tripping at 66 kV or 33 kV may be of more importance than, say, for example, your LT breaker tripping. Okay, so that substation breaker tripping you can configure to have a very irritating sound, so that immediately operator turns his attention. Similarly, for an LT circuit breaker tripping, you may not even have configured a sound. So that way, it is very configurable. Some different types of alarms I have listed here. Abnormality alarms. So normally all your devices will be in some state, and because of some abnormality, they move into abnormal state. So for example, your circuit breaker is normally closed, but because of a fault, it gets tripped and abnormally becomes open. Okay. Similarly, your earth switch, normally it is open, but when you want to ground a particular section, it is closed. So that is an abnormal condition. So whenever any device in the network moves into its abnormal state, alarm will get generated. So that is one type. Then command failure alarm. So an operator tried to operate one particular device. He tried to open or close a particular switch, but due to some reason, command has failed. So to denote that, and since that is a really important information, to denote that a command failure alarm will get generated. Similarly, loss of communication. When a substation communication is lost because of some issue in the communication equipment, alarm gets generated. Similarly, the number of times a device is operated, maybe due to maintenance purposes, you can only operate a switch 1000 times. So once that count is reaching 1000 or it has already crossed 1000, alarm will get generated. Similarly, limit alarms. So you can configure limits for your voltage and current or any analog data. So whenever values are crossing those limits above or below, limit alarms will get generated. Flatlining alarm means generally some values should not be constant. They should always keep changing. But for example, if any value is constant for some time, this alarm will get generated. Then rate of change alarm. Some values should not change too drastically. Like you are managing a 11 kV network, so voltage can go say from 11 to 11.2 or 10.7, but suddenly it shot up to 15 or 16. So that is not good. So those kind of things are shown by this rate of change alarms. Similarly, instrument failure alarm. So generally your measuring instrument will have some measuring range. Say for example, the voltage can be in the range of 11 kV, but suddenly it shows 66 kV. So something is wrong with the measuring instrument. So that time this kind of alarms will get generated. So these are, and there are many other types of alarms as well. At a high level, these are the different types. Okay. Okay, you keep getting so much of data from field, you also need to take care of its quality. So what is this data quality? It is some additional information about the data necessary for the operators. So it will answer questions like where did the data come from and what is the authenticity of that data. So for example, you get some value coming in from field, and then suddenly because of communication issue, now it's no more communicating. But still that past data, whatever came in last, that is still shown here. But it may be correct, it may not be correct, because when this loss of communication happened, during that time, value could have changed. So that means quality of that particular data may not be good. It can be questionable. So that way different quality types are also defined, and they are shown as symbols beside the displays and all your network displays and tabular displays, so that operators can take a decision accordingly whether to trust that data or not. And sometimes, like I told you, you may manually replace also. You know that some data is coming wrong, so you have manually inverted. So all those things you have this feature to show that in the display. Okay, then you have this tagging feature. So very simple example is that when you are in a hotel room, you can put those do not disturb tags in front or laundry service tags in front. Similarly, in our industry, say for example, a particular feeder is under maintenance. So in the substation, if you go, near that particular substation breaker bay, they put a do not operate tag. Okay, so similarly, that feature is available in this SCADA application displays also. So you can place a tag in the displays. Okay. So these tags are used to specify exceptional conditions on field devices and to inhibit control of those field devices. Okay. And they can also be used to enforce some business process. Okay. So for example, utility might say you are performing some maintenance activity, you have to place a tag so that other operators will know that something is happening. So those kind of things, it can be enforced. Okay. And there can be different tag types. So one example is do not operate tag, or do not open tag, or just an information tag, or live line tag. So that way you can have different types of tag. And this is how your tag looks like. Okay, so you can enter some notes and all those things. Why you are placing tag? Tag is placed by who? Tag is placed on what devices? All those kinds of. Okay. All the operators. I am placing a tag as an operator. Other operators can also see that information before they proceed to any operations on that particular network. So we talked about calculated points first. So what are these calculated points? They actually derive value by evaluating configured arithmetic expressions. Okay. So very basic example is that suppose you have a in the previous scenario you have a substation. So you have the 11 kV bus. You have one incomer and two outgoing feeders. Okay. So say for example, feeder 1 is having 30 amps and feeder 2 50 amps is flowing. So obviously by Kirchhoff's current law, incoming will be 80 amps. Okay. So for example, if you are measuring this current and this current, again you don't have to measure this current because addition of these two will be this value. Okay. So for example, after 10 seconds, this 50 amperes has become 24. So automatically your calculated data will also change based on real-time updates. This value will also change. Previously it was 30 plus 50, 80. Now it will become 30 plus 24, 54. So with this, you can reduce the number of telemeter points. So in a way, you are reducing the cost also. But again, this depends. Like if you have too many calculated points, too much of processing needs to be done. So your control center cost will increase. So that way, it is a call that has to be taken by utilities. So we have seen some high-level features of SCADA. Now we are moving into DMS. First and foremost, it is used for centralized user management. So you can create different users in this application. So for example, a new operator has come, so you can create a login for him, or the existing operator has been deleted, you can delete his login. Those kind of things you can do. Okay, and different applications in this DMS are compartmentalized into different user privileges. Okay, so some applications or some functionalities are grouped into a particular privilege, so that a type of user can be given only some privileges. It's not like every user can do everything in the system. Only what is required to them, that is only given. So that is called principle of least privilege. Only what is necessary is given to them. So that way maloperations or misuse of the system is prevented. Okay, and user action logging for auditing purpose. So everything that the operator does will be logged. The moment when the operator has logged in, when he has logged out, in between what all he has done, all those things will be automatically logged into the system. You don't have to maintain a separate logbook for them. Okay. So like I told you, user groups and different types of users can be created, and accordingly DMS will be shown to them. So for operator, it will look like something. For an administrator, it may look like something else. For a shift supervisor, it may look something else. So all functionalities will be varying based on what type of operator has logged in. Okay? Similarly, for network planners and network developers, etc. Okay, and then we are talking about the displays in DMS. They are nothing but an extension of the SCADA displays. But like I told you, because of integration with GIS, you can see the georeference network display of the feeder networks. According to their actual location in field, all your network equipment like RMUs, transformers, switches, conductors according to their actual path that are they are traversing into, they can be mapped into your network. Okay. And from this DMS will generally have capability to automatically generate schematics. Okay, schematics are more used for operational purposes. So here, when you look at this screen, you may not be able to operate or manage that network easily. But here in this screen, you can easily understand if the operator opens a particular device here, how is it going to affect the remaining network. Okay, so in this example, this is one feeder SLD. Each of this is one RMU. Okay, RMU1, RMU2, etc. And each of these is a distribution transfer. So from this, he can easily understand by operating a particular RMU, how is it going to affect the remaining networks. Okay. And all these displays are fully customizable and layered. So you can customize what you want to see here. You can say, for example, you don't want to see DTs in a particular way. You only want to see the RMUs. So you can turn off the DT layer. Vice versa. If you want to see only RMUs and DTs, I don't want to see the conductors. So you can turn on. What all you want, you can turn on. What all you don't want, you can turn on. Displays, labels, all those things you can turn on and turn on. They are very customizable. And land-based data can be superimposed. So like I told you, this is geographic in nature. So behind this, you can put Google Maps or any of those satellite information that is called land-based data. Okay, so that you can understand where they are actually positioned on top of Google or something. So that is also a big advantage when you are trying to send your field crew to a particular RMU. So you can easily understand, okay, it is near this junction or it is on this road, and you can easily direct them on phone. Okay, and all these displays, they will be linked to the substation SLA displays that are there in SCADA, so that you can easily interchange between one view and another. Okay, another important feature is area of responsibility or control zone. Okay, so you can, so like I told you, with distribution networks, you have vast network equipment to control. So sometimes the operator may be overwhelmed with the amount of data that is coming in. So to avoid that, you can divide the whole network into multiple zones and assign each zone to a particular operator. Okay. So in this example, if you see substation A, substation B, and you have two feeders connected in a ring. Okay. So some portion of feeder A, including RMU1 and 2, that can be grouped into a separate zone, and the other side of that feeder can be grouped into a separate zone. Okay. So you can call this area of responsibility 1 and AOR 2. So you can assign the control of this area to operator 1 and this to operator. So with this, what happens? Operator 1 will still be able to see what is happening on this side, but he may not be able to operate, so that he can focus only on what is happening this side, so that his attention is more focused. Okay. So these AORs, they can be defined across different substations, feeders, etc. So based on the utility requirement, they can even define AORs for each electrical section or each electrical distribution, whatever, or each substation separately, and so on. Okay. So in each AOR, supervisory control, data entry, alarm management, all those things can be restricted, like I told you. Okay. And these AORs can be operator centric or the machine centric. So either you can assign AOR1 to one particular operator, or you can assign it to a particular machine, so that another operator comes and logins to that. He will be able to control only that region. So that way you can divide and effectively manage your distribution network with the help of this functionality. Next one is temporary elements. So these are nothing but non-SCADA objects to mimic the temporary changes in the network. So for example, fiber cut, tree fall, using of a jumper because of some temporary scenario. All those kinds of things, obviously they won't be SCADA for conductors, so they cannot be automatically mimicked in the control center. But with the help of these temporary element objects, you can manually create them. So for example, you can manually place a cut in case of a tree fall, so that to denote that, okay, conductor has been cut at this point in the net. Similarly for other types also, jumpers, temporary groundings, temporary generators, etc. Okay? So all calculations, they take into account these things for also. Okay, so we will see next what all calculations happen. So then maybe another feature is trending. So if you remember, we talked about historical server where everything gets logged that is coming in from field. So historically, what all happened, you have access to that. Because of that, you can plot graphs or trends. Okay, so you can plot multiple values on a single graph. For example, voltage and current, or voltage or current and reactive power or real power into a single graph. Okay, and you can use that for different types of analysis. You can print them, you can export them, you can play around with these with various functionalities. So based on the requirement, you can perform accordingly. So that is trending. Then historical playback. So like again, historical servers stores everything that has happened in history according to its timestamp. So just like how you watch movies or something on Netflix, you can even go back to a point in history and play what happened at that particular point of time in the network. Okay, so when you play back to some past situation, it will not affect the real-time condition. Obviously, it is playing in a separate simulation mode, so that you can watch it like a movie. You can even fast forward it. You can go to a particular point in the network. So when this kind of things are done is when you want to analyze more on a particular system failure or fault event, you can go to a particular point in the history and study what had happened at that time. So that is historical playback. Then another important feature is interlocks. Okay, so interlocks are nothing but conditioned operations between status signals, where change of state of one signal directly affects the change of state of other signal. So for example, if you take this case, so this is a two-way RMA. So you have one isolator and its earth switch, isolator 2 and its earth switch. Isolator 1, you can consider this is in closed position, this is in open position. Isolator 2 is in open position, earth switch is in closed position. So I have denoted the same in this table. Okay. So now when this isolator is closed and this isolator is open, so when I try to close this earth switch, okay, so when there is the presence of this interlock, it will not allow me to do that. What it will say is that you cannot ground a live section. Since this is live, this is not isolated, you cannot ground that section. So it will not allow you to do that operation. Similarly, vice versa also. When it is grounded and when you are trying to close this isolator, it will not allow me to do it with the warning or information that you cannot energize a grounded section. So that way, again, safety is taken care of. So that is the interlocks functionality. Very important feature of DMS is topology processing. With topology processing, all the coloring of the network is managed. So if you remember in that geographical slide I showed you, you saw the geographical network like this and you see different colors. Okay, so all these different colors are managed by the topology processor. Coloring of the network displays according to real-time or current network conditions. So for example, if you have a ring between feeder 1 and feeder 2 and you have 4 RMUs, okay, feeder 1 is feeding through RMU 1, 2 and it is kept open at this RMU. Similarly, in the other direction, feeder 2. So the coloring is automatically done in such a way that in the first glance itself, operator will be able to understand, okay, feeder 1 is up to this point and feeder 2 is up to this point. So you'll have some legend or something to show orange color means feeder 1, blue color means feeder 2. So you'll have a legend to the side somewhere explaining this. Similarly, determine the normal and abnormal condition of the network with every status or analog value change. So the same network, you can color it based on energization, say for example. So in that case, green color means energized, blue color means de-energized and yellow color means grounded. So This part of feeder is energized. This part is also energized. Since both are energized, they are in green, even though they are fed by different feeders, but they are both energized. Okay. This section in between, it is de-energized. It is not fed either from this side or from this side. So it is de-energized. So it is denoted in blue color. This small section in between, that is grounded. Both switches are closed. They are isolated. So it is shown in yellow color. So that way, in first glance itself, operators will be able to understand which part of the network is healthy, which part is de-energized, which part is grounded, which part is meshed, all those things. Okay. All this information you can see like this graphically in those network displays. Similarly, you can see it in a report format also, okay, for exporting and all this. You can see it in a table. At any given time, real time, what is the topology positions, open, what is closed, all those things you can see in a table also. Okay, now we are talking about load flow analysis. So this is, you can say, a heartbeat. So now we are entering into the core DMS application. Okay, so until now we have seen all about displays and all those things in DMS. Now we are talking about the brain that is functioning in the DMS application. So the heart to all this thing is load flow analysis actually. Load flow or power flow, however way you call it. Okay. So you may be already knowing the definition. It calculates the steady state variables like voltage, current, etc. at all nodes in the network. Okay. So input is this. It takes in this data, voltage, source voltage, conductor impedance, and connected load information. And output, it will give all these steady state variable data across all points in the network. Okay. So why this is needed is, first of all, to perform any optimization or correction on the network, the whole network scenario has to be known. Okay, so you have substation, you get the data from there. You have RMUs, you get the data from there. But if you don't have RMUs, like in a conductor, you don't know how much current is flowing, right? Because there is no SCADA. So at any point where there is no SCADA also, with the help of load flow, the values are calculated so that you have the whole network information in front of you, what is there in the field, so that you can optimize accordingly. Okay, so known values are these, unknown values, load flow will calculate. It will run in conjunction with another application called state estimation. So we will see what is that next. Okay, so load flow, this application can be triggered either manually. So whenever operator wants, he can manually run load flow on a particular feeder or a substation or the whole city, or it can be configured to run periodically, make it run every 10 minutes, 15 minutes, etc. Or whenever there is a topology change. So obviously when a breaker is tripped or some device is closed or opened, so network scenario changes. So then also load flow has to be run to recalibrate the scenario in the control center. So then also automatically it can run. Okay. So like we told, load data is one of the known information. So how this load data is calculated is, you will have the KVA rating of the distribution transformers, and how this KVA rating is used while calculation is based on the load curves actually. Okay. So for example, you can have different types of consumers, residential or industrial or commercial, etc. So their behavior will be obviously different. Okay, so residential usage will be more in the morning and night. Industrial will be more throughout the day, like that. Similarly, based on the season also, consumption will vary. In summer, consumption will be of one pattern. In winter, consumption will be in a different pattern. Similarly, on a weekday and weekend, it will change. Okay, so for one type of load, in one season, in one day type, one pattern is followed. So like that, you can have different number of patterns to define the load curve. So at any given point of time, so load curve is nothing but x-axis is time 0 to 24 hours and y-axis is the scaling factor of the KVA rating. Okay. So at any given point of time, when you are running load flow analysis on a particular DT, first it will try to identify which load curve it needs to use for calculation. Then at that particular point of time, what is the scaling factor it needs? Those kind of things it will calculate, and based on that load flow is run. So the more the number of load curves you have, the more accurately you are denoting the load condition, and more obviously the output will be more accurate. Next, the output of load flow results. You can see them again graphically like this. So at each point in the conductor, you can see what is the current flowing, what is the direction of flow, what is the voltage, what is the active reactive powers, etc. You can see it in a graphical way. You can see it in a tabular format. You can see it in a table also. So both ways you can see the results. So we were talking about the other application which runs in conjunction with load flow, that is state estimation. At least with respect to distribution management system, state estimation primarily runs to compare the measured data and the calculated data. So like we already saw, current, voltage, those kind of information are measured in the substations. Sorry, I just need to power on the. So we are getting measured data from substations and different RMUs. Apart from that, load flow is also calculating the same data based on all the known values. Okay. So what state estimation does is it compares the measured data with the calculated data and matches them. Okay. So why it does is to identify any bad measurements, something is wrong in the measuring side or something is wrong in the networking side. Say for example, you wrongly drew the feeder. Okay. So because of that, some unnecessary mesh has formed. Because of that, measured data is correct, but calculated data is wrong. So that way, state estimation will compare both so that you improve the measurement side in the field and you improve the calculated side in the control center also. So the higher the estimation quality, the more the model network is close to the field condition. So your main aim should be when you are centralizing the operations, so you have to mimic exactly what is there in field. So with the help of state estimation, you will reach closer to your target of mimicking that. Okay. So one sample screen I have shown for state estimation. So you have this pie diagram showing the SCADA quality. You have n number of SCADA points reporting from field. So the more green color you have here, that means more quality of SCADA is good. So everything is reporting continuously from field and it is good. Similarly, estimation quality. So whatever you are estimating, the more the amount it is in green, that means the more your field and your control center are matching with each other. So that way it is running in conjunction with load flow and it is helping you improve the condition of the network in the control center. That is the next one. Then we are talking about this application called FLIZR. So that is, full form of it is fault location, isolation and supply restoration. So I can confidently say that this is the most sought after feature in DMS. Okay. So this application, it can be triggered either automatically or on request like load flow. It can be triggered automatically. Similarly, it can be executed automatically or manually also. So we will see that next. What is the input to this application? Input is whenever there is a fault in the field, this application will be used either automatically or by operator intervention. What is its output? Output is a switching plan for locating and isolating that fault which was there in field and restoring supply to the non-faulty segment. Okay, that is the output of this. So we are seeing different stages of FLIZR. First stage is fault location. So fault will be located based on two ways. One is based on the fault current measurements. So if you are taking fault current measurements at substation and at different RMUs, you can locate the fault based on those measured fault current values, or you can locate based on the fault passage indicator status. So I was talking about this fault passage indicator status initially when we saw RMUs. Okay. So normally they are in reset condition. So whenever fault current is passing through them, they automatically go into set condition. Okay. So for example, if you consider fault in this section between these two RMUs. Okay. So what happens immediately? Obviously, your feeder breaker will trip. Okay. But before that feeder breaker has tripped, some fault current was passing through this network. Okay. So fault current is passing through like this. It is passing through this FPA this way, passing through this FPA, and it is stopping here. Okay. So like I told you, FPIs will get set when there is fault current. So this will get set and this will get set. This will not get set. It will continue to be in reset position because fault current is not passing through this. Okay. So fault will be located between the last set and first unset FPA from the source in direction of power flow. So when you are going in the direction of power flow, it will identify the last set FPA. So this is first, this is second. So this is the last set, and then the first unset FPA. So this is in unset condition. So that way it will identify that, okay, this is the faulty section. So with one single RMU functionality, you are able to identify fault within a few seconds. So imagine in the previous days, from what I understood from one of the utilities, whenever there is a fault, there is a huge fault finding equipment which is placed in a truck, and they had to travel across streets and pass some frequency and get the resonance. So wherever there is fault, the frequency of resonance will change. So that way they'll go across the feeder network to identify. So imagine if fault is there in the last RMU and that feeder is 10 kilometers long. Sometimes it may take a day or two, but now with the help of this feature, it is just within few seconds. So that is the first part. So we have located the fault. Next part is isolating that fault. Okay. So now fault has been located. Fault isolation algorithm will run, and it will suggest the switching actions that need to be done to isolate the fault. For example, in this case, so previously both of them were closed. So it will suggest you to open both. So it will suggest you to open this and open this so that the faulty section is isolated. Okay. So again, this can be automatic or semi-automatic or manual. Automatic means, so whenever there is a fault, automatically fault is located, automatically system performs this. Semi-automatic means, when there is a fault, the operator will trigger this application. It will give you the result. It will say, "Key, open this and open this." Then operator will review that, yeah, this is fine. I can open this and I can open this. Then with one single click, he will open both. That is semi-automatic. Manual is, like I told you, operator can manually see which all FPAs are in set, which are in reset. He can only manually identify the faulty location and manually isolate. Okay. So here you can consider remotely controllable or manually operated switches. So for example, you have so many RMUs. So for example, this RMU is remotely controllable. So it is reporting to control center, but here there is no communication equipment. So this is not reporting to control center, and you cannot remotely operate it. Okay. But still, you can use this isolator to isolate this fault. How? By sending the field crew there and asking him to manually operate. Okay, but in that case, what will happen? Outage time will be increased. So to avoid that, for example, if the next RMU is remotely controllable, you can immediately open that. In that case, some more people unnecessarily they'll be under outage, but the other people who belong to non-faulty section, they will get restored immediately. Based on the requirement, the operator can take a call in this case also. So that is the second step of fault isolation. Then supply restoration. So restore supply to non-faulty section. So we have isolated the fault here. So we can restore supply to non-faulty section this side and this side, both sides of the fault. So that can be done by closing back the feeder breaker. Now since the fault is isolated, it will not retrip again. So this side supply is restored. Similarly, because of this ring structure, there is one more source available for supplying this transformer. So by closing that particular device, you can restore supply this side. So the supply restoration algorithm will suggest you the switching plan to restore supply. It will suggest you to close this. It will suggest you to close this device. Okay. So another option is there here. Suppose there is one more. So you see feeder 1 here, feeder 2 here. Suppose there is one more bay here and it is going to feeder 3. Okay. And that is kept open. So supply restoration algorithm will calculate both options. So it will see if suppose the supply is restored from this feeder 3. Okay. How is the condition? If the supply is restored from feeder 2, how is the condition? For example, if you restore from feeder 3, feeder 3 is overloaded and it is running at 120% load. But when you supply from feeder 2, it is only at 70%. So it will keep all those options in front of you. and you can take a call accordingly. Okay? Even though overloading is more, maybe because of some reason you want to restore from this field. So that way it will give you all those ideas in front of you. So like again, I'm repeating, it is like an additional brain. It is supporting the operator's brain in giving so many options. That is next step. Then once supply is restored in the non-faulty section, you send your field crew to the faulty location. They will try to clear the fault. Once the fault is cleared, you have to go put the network back into the pre-fault condition. So again, it will suggest you to do what all you have done previously. So it will ask you to close this, and open this. Okay. So that is the last stage, that is return to pre-fault. So this way you can easily identify when a fault has occurred, where it has occurred, isolate it, restore to the non-faulty section. Once fault is cleared, bring it back to the pre-fault state within few clicks. So that is why this is very important and probably the most sought after DNS application. Then we'll quickly see some other important applications. Next is World War optimization. So this is an advanced application that will help you manage and optimize the voltage and reactive power in the distribution network. Okay. So the resources, so previously in case of Flizzr, the resources were only switching devices. So it will output is, it will say open this device or close this device. So resources are only switching devices. In case of VVO, resources will be capacitors or tap changers or generators. Okay. So this World War optimization can be run at a power transformer level or at feeder level. So for example, on a particular feeder, power factor is low. Okay, you want to increase the power factor. So the system, this VVO will suggest you to introduce a capacitor somewhere connected in that feeder. So wherever you have multiple capacitors connected at different locations on the feeder, based on your requirement, it will suggest you to introduce 2 capacitors or 3 capacitors. Also the ideal locations of these capacitors. That is in case of war optimization. Similarly, if you want to increase the voltage, so it will suggest you to, at a power transformer level, it will suggest you to increase the taps. Say current tap position is 2. Based on your requirement, it will say increase it up to tap 5 or 7. So that way, it will suggest the increase in tap changes, increase or decrease. That is World War optimization. Next application is load shedding. So we as energy consumers hope that the utility do not use this application, because obviously we don't like getting into an outage. But for an operator or for the distribution utility, it is very important because it has so many features. So with this application, they can shed load in case of emergencies and restore the load once normalcy is reached. Okay. So there are options to do cyclic or non-cyclic shedding. So you can rotate the shedding, like shed a particular feeder, after some time restore it, go to the next feeder, restore it, go to the next one. That way you can do it in a cyclic fashion, or shed all the feeders at a time and restore all of them at a time. That is one option. You have the options of frequency based or time based shedding. So you can set the frequency limit, say 49.8 or something. So once frequency goes below that value, automatically system will shed the configured feeders. So you have to configure before which feeders system has to shed. And once again, once it goes above that limit, they are restored automatically. That is frequency based. Time based means due to some emergency, you want to shed 5 megawatt for say half an hour. Okay, so you will select which feeders you want to shed, and you will say shed it for 10 minutes or half an hour. Then during that point of time, it is shed, and after that time, automatically they are restored. So that is time-based shedding. Then this shedding can be either automatic or manual or periodic. Automatic means like in case of frequency, automatically when it goes below a limit of frequency, load is shed and restored. Manual means in case of time-based. So at any given moment of time, you get a requirement to increase the frequency and reduce the load. So that time manually you shed some feeders. Okay. Periodic means you can create some load shedding schedules. Say for example, a particular industrial feeder, you shed it between 2 to 5 on every Saturday. Similarly, domestic consumers feeder on a particular day, on Sunday you shed it between 5 to 7. That way you can periodically configure schedules and shedding will run during those periods. That is that one. then all these types of shedding will be running on different criteria, like for example, number of customers, priority of customers, history of outages, etc. So for example, you have 10 feeders to shed, okay? So the feeder which has maximum number of consumers will be shed at the last. You consider this number of customers criteria. The more the number of customers, you don't want to shed it, so you put it at the last. Similarly, priority of customer. So for example, there could be a feeder with only 10 consumers, but 2 of them are hospitals, so they are very high priority. So even though number of customers is less, because the priority is more, you shed them at the last. Maybe there is an opportunity that already you have achieved the requirement and you don't have to shed it. So that way they are put at the last. Other option is history of outages. So there could be only 2 consumers in a feeder and both of them are not hospitals or lower priority consumers only. But in the past 10 days or 1 week or whatever, already they had so many outages. So again, it won't be good if we shed them. So you can put that at the last. So that way, it gives you so many options for shedding and restoration. Okay. That is load shedding. Then next option is network reconfiguration. This is also an advanced application used for suggesting optimal tie open points to reduce overloads in network, minimize the losses, and improve the feeder or transformer load balance. Okay. Output in case of this application is again a switching plan containing close and open operation. So it will just say, again, this can also be run in automatic or manual. Okay. Again, this example, if you take, you have feeder 1 in orange color, feeder 2 in blue color. There is a tie open point in between here. Okay. So output of this network reconfiguration will always be to shift this open point this side or this side. So why or how it should shift is, for example, in this case, say this power transformer is of 200 kVA. Okay. So feeder 1 is feeding 3 distribution transformers of total 200 kVA. So in this hypothetical scenario, it is at 100% loading. Okay. Similarly, if you see this side, it is a 400 kVA power transformer and feeder is feeding 5 DTs of 50 kVA. So that is 250 in total. Okay. So this is running at 100% loading and this feeder is running at maybe around 60% loading. So when you run this network configuration either automatically or manually, it will suggest that this is getting overloaded. Please shift some load to this feeder. So that way it will say, okay, you open this switch and close this switch so that this transformer will now be fed by feeder 2. So 50 kVA will go from here to here. Then it will be 150 out of 200 and this will be 300 out of 400. So in this way, overload is reduced this side and they are also equally balanced. They are both at 75% load. Okay, so based on your requirement, network reconfiguration can be run. So this is one more advanced feature. Next feature is reliability analysis. So this is again an advanced application which is used for calculating reliability indices. Some examples are SIFI, SIBI, KIFI, KIBI, etc. SIFI is System Average Interruption Frequency Index, and this is System Average Interruption Duration Index. This is Customer Average Interruption, both frequency and duration, and this is Momentary Average Interruption Frequency Index. Okay. So different utilities may have momentary outage definition differently. So for example, utility can say 10 seconds or lesser will be momentary. Another utility may say 1 minute or lesser can be momentary. So that way, if the outage is more than this duration, either 10 seconds or 1 minute, it is considered as a sustained outage and it is going into these calculations. If it is lesser, it is going into momentary calculation. Okay. So example, I have given a formula. SIFI is, so SIFI will give you in general the number of interruptions that have occurred on a particular feeder. Okay. Formula is total number of customer interruptions by total number of customers. So if you cancel the number of customers, you see interruptions. I am explaining you in a crude way. SIFI value will be approximately the number of interruptions occurred on that particular network. Similarly, SIDI is the duration. Total number of customers, if you cancel out, what is left is duration. So the value of SIDI on a particular network will be, for a particular time period, will be the duration of outage over the, so for example, SIFI value is 5 and SIDI value is 5 for a particular network. So that means, and for a particular month. So that means for that feeder in that particular month, 5 times outage was there, denoted by Psi-P, and the duration of 5 hours in total of outage was there, denoted by Psi-P. Okay, probably each outage 1 hour duration, 5 times outage and 5 hours outage duration. That is total. So this way, the performance of a distribution utility is measured by these indices. Okay, so they can be calculated in history also because of the historical server. So at this moment, I can calculate the Psi-P values of last year, May or June of a particular feeder. And generally, these are used for regulatory compliance. So each utility will have to submit this data to the regulatories for their assessment. Okay. Then switching plan and safety management. So generally, with the help of this SCADA DMS application, whatever future maintenance or ad hoc field maintenance activities, you can easily plan them and execute them according to a plan. Okay, so that way you manage everything well. Okay, you can even define some life cycles to adhere to utility business process. For example, you can create a switching plan is initially created by someone, then it is reviewed by someone, then it is approved by someone, then it is actually executed by an operator. Okay, maybe it is cancelled because of some scenario. So that way the whole life cycle is maintained in the system for tracking purposes. Okay, these switching plans can combine telemetered and manual switching operations. So for example, in this example, you take a particular load break switch is being opened, another load break switch is being opened, earth switch is being closed that way. So with that, maybe a section is being isolated and earthed, then the actual maintenance activity is carried out, then again reverse of this is happening. Opening of earth switches and closing of the load break switches. So probably this switch could be remotely controllable. So operator will just open from control center. This may not be controllable. So he will talk to the operator, the field crew on phone. He will ask him to open it. Once it is opened, he will manually change the status here. So that way everything is done in a coordinated way. Everything is recorded also. Okay. Safety documents can also be managed in this feature. So you can assign some safety documents like permit to work, clearance or something like that. Okay. And switching plan can be done along with tagging. So whenever some maintenance activity is happening and the switching plan is created, automatically tags can be placed to denote that there is some maintenance. Similarly, return to normal steps can be auto-generated. So for again in this example, tags can be added. So when you are opening a load break switch, you will add a do not close tag so that another operator will not accidentally close it. Like that, tags can be added for each operation. Then safety document can be issued to the field crew. Okay, so it could be some code or something, whatever. It could be a document printout of something with instructions of what to do in the maintenance activity. So that is issued. When actual work is carried out in field by him, then he will return the safety document. So that document is returned. Then return to normal steps. So it will be exactly the opposite of what we have done. So that is automatically suggested by the system. So that way it is very easy to manage all the maintenance activities with this feature. Next one is DTS. DTS stands for Dispatcher Training Simulator. So you have seen there are so many functionalities and so many optimizations and analysis applications that are running. Okay, so obviously new operators have to be trained before they sit in front of the real-time system. So for that, there is a training environment provided for the operators to acclimatize to the DMS application and also to see different real-time scenarios. Okay, this DTS environment is completely isolated from the real-time system for security purpose, safety purposes. Okay, so you don't have to fear in simulation environment, if I open or close something, will it affect the field? So it is completely isolated. You don't have to fear about it. Okay, there is a simulation algorithm running here which will substitute this SCADA and field updates. So in real time, you have this SCADA that is pumping in so much of data because it is connected to field equipment. DTS is not, but it has a simulation process running there which will simulate all these field conditions and show. Okay, so this DTS consists of two machines. One is a trainer machine and other is a student machine. Okay, trainer can create real life like scenarios on the fly, or he can create some scenarios in advance and play them out so that students will see them all like happening in field and they have to react to. Okay. Some examples of scenarios could be loss of communication of a particular substation, loss of command of a particular device, overloading of a particular transformer, transient or permanent faults occurring. Okay, these kind of events trainer can simulate and see how the students are reacting to them. Okay, then students can be evaluated based on their reactions to these simulated conditions. Okay. So to compare both the environments, this is how it looks. So in real-time environment, you have the field devices. SCADA is pumping in data from them. So in different servers, they are processed, and finally they are shown in the HMIs in front of the operators in their computers. Okay. Similarly, in case of DTS, there is no connection to field, but in substitute to field, you have the trainer workstation. So he is creating so many scenarios. He is tripping a breaker. He is adding a loss of communication event. He is putting a transient fault, those kind of things. Those events are processed in the simulation server and they are shown in the displays of the students. Then they have to react accordingly, how they are going to react in the real life scenario, so that they are trained accordingly, similar to what is going to happen in the field. Okay? That is DTS. Similar to your SCADA summaries, what all displays you saw in geographical format, you can see them in reports also. So here some useful reports could be abnormal topologies. So in one single report, it will list all abnormal topologies, like which particular tie point has shifted, which ground switch has been closed, which breaker has been tripped. So in one single table, you can see all the abnormalities in the network. So if the table is empty, that means your network is in normal condition and you don't have any work. Okay, so that way you can easily identify. You can even represent the whole DMS network model in a tree format. Substation, below that power transformer, below that feeder, below that RMU, in a tree structure you can show in a report so that you can get easily acclimatized. Okay. Various other calculations, operational losses, what are the losses accumulated over a period of time for a particular feeder historically, those kind of calculations. What is the voltage imbalance, what is the load imbalance, those kind of calculations could be done. So all those things you can report, take a print, and you can discuss with other operators, you can plan for new maintenance accordingly. So many things, so many possibilities are there with this functionality. Okay. So I have only shown some of the important features. So these plus many more features that make the life of operators easy and equip them with enough tools and capabilities to take good care of the distribution network. So like I told you, DMS is a good brain and it is a very good brain which is supporting the operators. Okay. So some of the common business use cases for distribution network. So utilities who have implemented this SCADA DMS applications, what are the most common features that they are using? They are using Flizzr to reduce the outage times, locating fault, isolating, restoring supply, all those things. Okay. They are improving the load balance, all those things, reducing overloads. They are using this network reconfiguration application. They are using all the events and master logs. Everything that is happening in the system is logged. Okay, so that is called event or master log summary. So they are using that for auditing purposes. So previously everything they had to note down in a register. Now they don't have to do it. Everything is automatically done. Then they are using the SAIFI reports for regulatory compliance. So they are submitting these reports on a monthly basis or a quarterly basis for compliance. Okay. They are planning so many maintenance schedules through this work order or switching management. And they are doing all the unplanned maintenance activities remotely. Previously, they had to go there, they had to send someone and do it. Now they are remotely managed. So these are the most common features that some of the utilities are using from this SCADA DMS application. Okay, so very quickly I will talk about the overall smart grid architecture. So until now, what we have seen is only these two, distribution SCADA and DMS. So you see there is so much more to what is happening out there. So we have substations and smart RMUs in field. So you have one system called substation automation that is installed in substation itself. It is, you can say, like a miniature version of SCADA, wherein you can only control the substation equipment, nothing outside the substation. Okay, that is there here. Then transmission substations communicate through transmission SCADA to EMS, energy management system. Distribution substation and RMUs communicate through distribution SCADA to DMS and OMS applications. And then you also have distributed energy resources or renewable energy sources these days. So they are connecting to a system called DERMS, Distributed Energy Resource Management System. So that is again talking to DMS. So this will also be part of ADMS. So together, this is all, you can call it as operational technology. So you also have some information technology systems that are supporting this. Okay. So on the other side of the spectrum, you have smart meters installed at our houses, replacing your conventional manual reading meters. Millions of such meters are communicating to a thing called head-end system. So they are concentrating data from millions of meters. They are processing it at a very high level and pushing it to this meter data management system. So here all the load profile and the billing calculation cycles are all calculated here. Then that is forwarded to billing center. So this is where, this is the application which is responsible for handing out the bills to the consumers. Similarly, this is talking to customer information system also. This is where contact details of customer, this is kind of a database. Each customer, his name, address, phone number, all those things are maintained here. So it is talking to MDMS. Then you have the customer care center. So this is like a call center. So whenever there is an outage, generally when you call the utility, the call gets logged in this customer care center. So it is connected to this MDMS also. Then you have this geographical information system. So this is where the distribution utility manages its network assets. So it is mapping all the network assets according to their geographical location in this GIS application. Okay. So from here only we are getting the geographical displays in PMS. These days, even ERP systems, enterprise resource planning systems are also coming up to manage the business processes and finances involved in those. Okay, and internally, IT systems and OT systems are talking to each other. So I can indirectly say we have only discussed about a drop of the ocean. There is so much more to learn about. Each and every system of this is very interesting, and each and every of this system has a very bright future, because nowadays all utilities are forced to becoming smarter. So they are in a way being forced to use this application. So it is always good to deliberate more on these. Maybe you can Google more on this stuff and get acclimatized more on the equipment, on these applications, because not only, so like Sandeep sir was saying, not only companies like product companies like Schneider or GE or ABB who are owning DMS or OMS products, even service-based companies like TCS, Infosys, etc., they are also opening a utilities wing. So they are providing services to the vendor companies. So there are so many opportunities even in such companies. Okay. So this is a very promising area. So I have personally been working since the past 10 years in this industry across multiple such systems. And I am very passionate about the work that I have done. So I hope I could garner some kind of interest in prospective students in any of these systems. Okay. So I'll stop the presentation by talking about what is the current distribution scenario in India with respect to SCADA and DMS. Okay. So private utilities, they are very less in number, as you know, but utilities like Tata Power Delhi, Tata Power Mumbai, and some state utilities like Karnataka and some utilities in Odisha, they are implementing this GIS and SCADA DMS systems on their own with their own money, based out of their own interest. Other state utilities are implementing these along with other smart grid technologies, which we have seen in the previous slide. They are doing it in a phase-wise manner with the support of Government of India through Ministry of Power and Power Finance Corporation. Okay. So this Ministry of Power has come up with this RAP-DRP initiative. So it stands for Restructured Accelerated Power Development and Reforms Program. So the main focus of this program is to reduce the aggregate technical and commercial losses. So they'll fund this project, and once it is implemented by the state utilities, so the result is verified by PFC to check whether actually AT&C losses have been reduced or not. That means whether effectively the grant has been utilized or not. Okay. So target AT&C loss reduction by 3% for those utilities which are posting 30% above losses. So utilities which had an AT&C loss of above 30%, target for them was set as reduction by 3% per annum. For those below 30%, reduction target is 1% per annum. Okay, and the eligibility for this program was the city or town had to have a population of more than 4 lakhs plus energy input needed to be more than 350 mega units. Okay, with that eligibility was met. So 72 towns across the country were eligible for this, and different companies had implemented their own SCADA applications. So it was implemented in two parts, Part A and Part B. Part A included establishment of baseline data, that is first implementing GIS and then implementing BMS and then other IT-based customer service center, etc. That CCC which we were talking about. Then Part B was about strengthening the distribution network. Okay. Then one more scheme that was brought up by Ministry of Power is this Integrated Power Development Scheme. So this is more about, so RAP-DRP was a little bit old, probably it came up in late 2000s, around 2008 or something. IPDS is much more recent. IPDS included strengthening of sub-transmission and distribution networks in the urban areas, metering of all the DTs and feeders and substations and consumers. Okay, and whatever projects were not completed in RAP-DRP, carrying forward them through this IPDS scheme, and introduction of ERP and other IT systems to other towns where was previously not implemented. So that is part of this IPDS scheme. Okay, one example scenario I'm going to share. So this RAP-DRP, as part of this RAP-DRP, Bihar State Utility, that is the South Bihar Power Distribution Control Limited, had implemented SCADA DMS system in Patna. So this Patna control center was commissioned. As part of that, 51 RTUs from 51 substations feeding to 216 feeders were remotely communicating to this control center. At the same time, some 305 FRTUs and probably about 600 overhead FPIs were also reporting to the control center. So overall, some 35,000 SCADA points across these components were reporting to the control center. So a data recovery or disaster recovery center was also commissioned in Gaya. So main control center in Patna and disaster recovery center in Gaya. Okay. All the backup of this data was being stored in this DR center in case of some failure. So Messrs. Schneider Electric was the SCADA implementation agency for this state. Similarly, Kerala State Electricity Board also, as part of this RAP-DRP program, had implemented SCADA DMS. So here 3 control centers were implemented, one in Trivandrum, one in Kozhikode, one in Ernakulam. A total of 50 substations, around 450 feeders, feeding around 1.5 consumers who are mapped in SCADA DMS across 1.2 lakh SCADA points reporting to the control center from these 50 RTUs and near about 3000 FRTUs. So this much of data was coming in from feed in all 3 control centers put together. Okay. Here the data recovery center is, so generally data recovery center is put in a different location, not where, which is not in the main center because of some earthquake or something. At least that center is safe. Okay, so this is in another location, and many integrations were done from SCADA with GIS, integration with the state load dispatch center over this inter-control center communication protocol for load shedding and some other applications. Integrations with customer care center and billing center. Now the new new initiative by the government of India, that Smart City 100 Smart Cities project came up in Cochin. So integration of the SCADA DMS control center in Cochin was also done with this Smart City control center. So these many integrations were done. Okay. So as a outcome of all these things, so at a very high level, I can clearly show you that the aggregate technical and commercial losses have been coming down. So this is in case of Bihar. This is in case of Kerala. Since already it is low, the reduction is not much, but in case of high losses in Bihar, the reduction is almost reduced by 30%. So I can confidently say that this application has helped the utilities and helped the government in improving the distribution scenario. So with that, I finish my presentation. Sorry for eating up some of your question and answer time. And thank you for listening to me patiently, and thank you Sandeep sir and Dhanu sir for providing me this opportunity. So now I open the session for any questions or doubts or deliberations. Thank you.
Okay. Mr. Praneeth, it's nice presentation and a lot of informative and knowledgeable, that you have shared with us. Actually, really, I see that what are the technical advancements in in electrical engineering that we'll be able to observe a very important point from your presentation. And also, I see what are the state of art. I can say that. Okay, what is the state of art in SCADA system? What the implementation status and all. Really, it's happy to know today some of the good points even for me also. So thank you.
Thank you so much.
Yeah. Now I request other members, please interact with the speaker if you have any questions, please. Sir, Banu sir, if you provide your valuable feedback, I think it will be help us.
Yeah, I think we'll wait for the questions.
Yes, sir.
Definitely, it is a very good question.
Thank you.
Yes. Yes.
Yeah. Hello, sir. Am I audible now?
Yes, yes. Please proceed.
Yeah. Thank you so much. So thanks, sir. Thanks for the informative session. It is very much useful for us, especially for the SCADA side. So we would like to know what is the implementation, what is the role of machine learning as well as artificial intelligence in SCADA side, especially for the Indian scenarios.
Okay, so as far as I know, as of now, machine learning scenarios are not yet been adopted by the state utilities, but yeah, definitely private utilities are thinking in that manner. So there is one more system called asset performance management. So where I can say like based on the past scenarios, it will predict what is going to happen in the future. So predictive analysis is done. So
yeah,
I'm not very sure about those APMs, but that is where machine learning is coming into picture in our country. So it is still in a budding stage. So probably in the coming years, it will take up much more space and time.
Hello.
Okay. Thank you, sir.
Hello.
Yes, ma'am.
Sir, I'm having one small doubt related with energy management system. Sir, is energy management system is applicable only on distribution generation side, or can I apply both distribution generation and demand side management?
No, energy management system is generally used only in case of your transmission and subtransmission networks.
So it cannot be suitable for distribution systems, sir?
Yeah, because the network conditions and connectivity is completely different. So features that are there in EMS are specific to some very limited network conditions. So generally it is not used in distribution networks.
Sir, suppose I'm having one microgrid setup. Can I use EMS?
It depends actually, depends on the particular use case, because yeah, definitely EMS can be used in place of microgrid, but again, what functionality you are targeting out of this microgrid, based on that you need to go for a DMS or EMS.
Okay, thank you, sir.
Yeah, thanks.
Okay. Any other questions, please?
Hello, myself Koteshwara Police sir. I have some clarifications and doubts. RMU. For example, may I know specific application for RMU? I mean that in overhead and underground. Hello, sir.
Specific application as
yeah, I mean, for example, if you see nowadays in the smart cities, and if you see the smart cities, majority of the cities is going for the underground.
Correct.
If we go for the underground cabling, the RMU will be efficient. to control and monitor. So,
Correct.
so if some of the cities like hilly terrains, some of the cities like northeast hilly terrains, it is not possible cabling. There the system will be the overhead system. So we can use
Right.
the RMUs there also.
So there in that case, probably you would prefer to have, instead of a single RMU unit, you would prefer to have, so we talked about the different components in the RMU, right? So the FPIs,
Yeah.
disconnectors and all, sectionalizers. So there you could go for a different implementation, like instead of one single unit, so that it is easier to mount on the overhead network. So FPIs can be separately mounted wherever you want. Switching devices can be separately present wherever you want. So that way, it is probably better to go not to go for RMUs in case of overhead networks, or rather go for
Not going for the
yeah.
Okay.
Yeah.
So for example, if we are not going for the RMUs, how can we control the 11 kV feeders? If we go for the DMS, in addition to the SCADA, how can we monitor and control the 11 kV feeders without?
So generally, for example, what you told is very much right. So for example, in Kerala, because the state is advanced, all cities are having underground networks. So the whole network is comprising of RMUs. But in case of Patna, there is some overhead network. So there, what they did was FPIs, individual overhead FPIs were installed, and individual sectionalizers were only installed, which were manually controlled. So there were no remote operations in those places, but they were manually controlled.
Okay. So
But
it's
still
like
they can be managed from the control center. Yeah, it is like a handicap, but still it is at least better than not having DMS kind of.
It's like general sectionalizers, which you mean that, right? General sectionalizer,
Right,
where
right.
the if we go for the ring main system, it is a general sectionalizers,
Correct.
right?
Correct.
Yeah. Okay.
Right.
Yeah. Yeah. And one more doubt I am having, sir. For example, we have, for example, 10 distribution systems, 10 distribution substations. That is by 33 by 11 kV. 33 by 11 kV.
Okay.
We are planning to install the SCADA in the each and every substation.
Okay.
So if we want in the same substations, we can have a each and every substation DMS, or either we can choose in one DMS. We can control all the substation in the same substation. How can we plan for this application, DMS application?
So
you got my point.
Generally,
right?
if you have this, I got your point. So generally, if you have these 10 different substations, generally if they are interconnected, so it is always good to have a centralized control center wherein everything is controlled from there. But otherwise also, even if you don't want to have a central control, I was talking to you about this substation automation, right? So that is there independently in each substation. So it is like a lighter version of this SCADA DMS application. So it is cheaper in cost also, but functionality also will be lesser. So you can install independently in each substation, but you cannot use the data of one substation in the other substation. That is the drawback of that.
Okay, sir. That is okay. The smart city aim, that is saying that we have the smart grid control center. That means that in the smart grid control center, we can monitor and control all the distribution substations as well as till the consumer end. In that case, how can we plan for the smart grid control center? So sections we can monitor and control in the smart grid control center.
Okay, maybe I'll just read. So basically, again, you need to go. So in that case, to have a centralized smart city infrastructure, you will need a centralized SCADA DMS solution catering all the distribution substations, and you will also need the AMI, advanced metering infrastructure. So that will include the smart meters at the customer level, and in the control center, you will have different system, hidden system, meter data management system, those kind of things, and all these things will be talking to each other, integrated to each other. So that way you can implement an overall smart grid.
Yeah, you
Yes.
mean that without SCADA in the particular individual substation, we can particular substation through the smart grid control center, right?
No, we need no. Without SCADA, we cannot control. We need to have SCADA in all the substations and one central distribution management system which is taking data from all the SCADA equipments in each substation.
Okay. First, we have to implement the SCADA and
Yeah. Okay. So yes.
Yeah.
Yes. So if I say like the order of implementation, first I would say you have to map all your network assets. So that means you need to have a GIS, geographical information system. Then you will start with implementing SCADA in all the substations. Then you will implement a DMS to take all data from different substations, and then you will work on the metering side.
Okay, so you mean that after implementing the SCADA in each and every substation, we have to make one new control center to monitor the substations as well as the consumers, like metering system. We need to have the dedicated control center, that is the
Yes.
whatever it is, what is a smart grid control center or with DMS application, right?
Correct. That's correct.
Okay. Also, okay. I'm taking more time. Sorry for that. There is
no
one more. Yeah. See, for example, what I say in that hilly terrains, is there any solution instead of RMU? How can we control the 11 kV feeders and the further OMS in the outage management, the 415 volts level? How can we achieve this without RMU? Is there any other alternate solution for that one?
Yeah, so like it, okay, so as far as I know, apart from sectionalizers, you'll have some smaller controlling equipment which have the communication capability also, which may not be as big as RMUs, similar to your overhead FPS.
Okay.
So in those cases, probably you can go for those kind of equipment. And when you talk about OMS, SCADA is not mandatory, but it is always good to have SCADA because OMS is more about finding the location of outage from customer information. For example, you get a call from one customer that there is an outage. You get another call from another customer. You see these two customers are connected to one fuse or one particular transformer. So that way you can predict the location of the fault. But if you have SCADA, it is very much easier to pinpoint the location. But even without SCADA, OMS can work. So even in hilly areas, you can have OMS working independently.
Okay. So for this OMS, we can have the separate control center that is like a smart grid control center, in your opinion, right?
Yes.
Really to clarifying my questions. It's a nice session. Yeah, thank you.
Okay, next. Any questions further? Okay. Okay, fine. If no questions, we will end this session. Okay. Banu sir?
Yes, sir.
Yes, sir. Shall we end this session, sir?
Yes. Pranit, really
Pranit.
very good, excellent presentation. Simple and beautiful, and very, very interesting. But for time, I think we would have continued. Excellent, really, very, very good.
Thank you so much. Thank you.
Thank you, sir. Thank you.
Okay, sir. Yeah.
Thank you. Thank you, sir.
Thank you.
So now I propose the vote of thanks formally for this session on behalf of IEEE Vizag Base Section and IEEE Power Electronics Industry Application and Power and Energy Joint Chapter. Heartily thankful to today's speaker, Mr. Pranit from Schneider Electric. So thank you very much, sir, for agreeing for our invitation and deliver a wonderful presentation to our participants today. And definitely, actually, we will arrange one more lecture maybe probably in early 2021. And actually this is where actually I see a lot of gap between the academics and then industry. Actually you have spoken with a lot of real examples how the electrical systems are upgrading nowadays, actually, particularly. And really you don't get this kind of information in the textbooks or well as by any other academic person. And this is how we will try to definitely bridge the gap, industry and academia through you. And definitely we'll contact you, sir, again. So thank you so much and for attending, joining for our event today, so as a speaker. And I thank all the participants for participating there, and then spared their valuable time today, even though today's festival time. And I wish a happy Diwali to all of you. And thank you all. Thank you all.
Thank you.
Thank you. Thank you very much, sir. I wish you the same to you, sir. Thank you, sir.
Thank you all. Yeah.